All right. My name is Rustan Leino, and I'll be giving the first part of this talk. Chris Hawblitzel will be giving the second. We had originally thought that maybe we would even have a third speaker give some part of it, Brian Parno, but he was out having a baby last week, so he's not going to be presenting today. What we're looking at is using languages for making sure that programs really are correct. And so let me say more about that. So if you look at what programs are developed, you can divide them into a number of categories. Here are three categories that you might consider. And so here I wrote casual, meaning programs that you would write in, let's say, in Excel or maybe Dancing Clowns on web pages, things that are programs and lots of people write them and perhaps they don't even think of themselves as programmers. And you probably, you'd like them to be correct, but you don't really care, right? Then there are the professional programmers, which are, I would say, most people at Microsoft would fall in this camp. And that's where we have, where there's a cost to having bugs in programs. We'd like to have them as bug-free as possible. And then there are mission-critical things that you might think of as the ABS systems on your cars or some system to make sure that some power plant won't melt down and things like that. So from the research standpoint, what we're doing is developing tools to help with these sorts of things. And they've been traditionally helping at the mission-critical parts, that is, making sure that programs really are correct at that level. And the reason for that is that at that level, correctness comes at such a price, that is, you're willing to pay the price just to make sure that you get correctness. But we're moving that up into the professional area as well. So what kind of target do we have? Well, if you're writing a critical program, and there are a number of those programs being written at Microsoft as well, that is, that maybe they're not mission critical in the same sense as I conveyed, but they're critical programs that you really want to make sure are correct or that are very difficult to test in other ways. But actually, let me mention as a note before I go on that another target really for these things is education. So in the main tool that I'll be talking about, Daphne is being used in many universities today. So it's, I know at least 3 universities, one in Moscow, Imperial College in London, and Rice University that are using Daphne in courses that all computer science students have to go through. And there are many other universities using it in optional courses like CMU, Caltech, Kansas State University. Actually, the list is long. So what's going to happen is that in another generation, when these people come out, they will have seen these sorts of tools, so we can do more things with them. Okay, so what I'm going to do is I'm going to talk about some tools that we are making in our research group. And I just made this slide to show a few of them. So I'm going to be talking about Daphne today, and then Chris will talk about Daphne and Boogie x86. There's also, so those two languages are for the Daphne programming language and for, well, a variation of x86. And VCC is for C programs. I will not be talking about that, but if you like the sorts of things, oh, hello, Papa. There he is. So if you like the sorts of things that I'm presenting, you could also look into the VCC tool if you're programming in C. And there's also F-star, which is being done in our research group as well. And they're both building on lots of infrastructure that we have that we've also developed. Okay, so what I'm going to do is I'll give you a small demo to show you what sorts of things I'm talking about, and then I will give you an example that I'll just show some pieces of in the Cloud Make verification. I'll say more about, and then Chris will take over and talk about Ironclad and how these tools are used in that project. Okay, so. So what I'm going to do is give you a small demo, and this demo was prepared as a demo that was going to be part of an Ironclad demo to demonstrate what Daphne was doing. So this piece of code was not actually, it's not actually part of the Ironclad project, but it could have been in principle. Now the interesting thing is that when this little demo was developed, the person doing it actually introduced an error in the code, and I will actually mimic that error here as well. Okay, so you can write specifications and code, of course, in many different styles in the language, just like you could in any kind of language. But let me show you the particular style that's used in a number of places in the Ironclad project. So at the top here, you can see a data type being declared. So data type, if you're used to a language like ML, you know exactly what I'm talking about. If you're not, you can think of it as an enumeration where each enumerated value has some value attached to it. The important thing here is that such a data type is a value type. But it can contain things like a pointer to an array, I mean that is in the usual sense, and also length. So this is really, it's a record, it's a value type record, or a struct, if you will. And it has an array, and it has a length in it. Now, if we're developing a program, we might not be interested in all sorts of records like that. We might want to have some restrictions on what the array is and what the length is. Maybe the length should say something about the array. And to do that in Daphne, the typical thing to do it is that you declare a predicate. Here I'm calling the predicate valid. So valid takes such a log struct, a log record, and it says that the log is valid if its array is not null and the length stored in the log is within those two bounds. Okay, so that's up to my discretion. The language does not tell me how to do this. This is a design decision that I may want to have about my program. So I say that's what makes a log valid. So you can have logs that are valid and logs that are not valid. Okay? Now, a log also, since it has an array and it has a length, really it represents some sort of mathematical value. And you don't always bring that out to the forefront in programs that you write. But in this little program, it is brought to the forefront by this function called value. So the function called value, what it's doing is it's returning a subsequence or a subarray as a sequence. So it takes the log.len elements beginning at index 0 in that array. And it returns them as a sequence. That construct gives you sequence. So what is a sequence? A sequence is a mathematical sequence. It's a value type. So it's not something that you store in a heap or whatever, like an array, but it's a value type. So those are very good in writing specifications, because having mathematical sorts of things in specifications is typically nice. Okay, so here we can then say what makes a log valid and what is the sort of abstract value, if you will, of the log. Okay, I'm going to define one more thing, and that is a predicate extends, which is given a log and an additional entry, and it's going to produce, or it's going to see if the out log is the same thing as the in log appended with the entry. And the specification, that is, the definition of that predicate is real simple, right? In fact, probably in a case like that, there's no reason to write a separate predicate that you would name in this way, but that's how I'm doing it in the demo. So I'm just saying that that extends predicate holds if the out log is the input log plus the entry. Okay, any questions so far? All right. Okay, so here, let's write a piece of code. So this piece of code is going to be a method. So in other words, some code. So this code has, as you can see, it has a precondition that says that we're going to start with a valid log. It has a postcondition that says that we're going to return a valid log. So the Daphne language has both input parameters and output parameters, just like in C#, but in C# you would list them all together and you would put out in front of this guy. And there's also a modifies clause which says what's being modified, like in system C# where you have to say various things that could be modified. That's similar here. And there's a postcondition that says that what we want in the post state is that the value of the new log is the extension of the input log followed by entry. Okay? All right, so to save myself a little bit of time, here's some code that purports to do that. And you can see that, well, let's take a look at the code. The code first checks to see inside the record, the given record, the log, if the length of the, if the number of slots used in that array is less than the length of the array, then we can put the next element there, right? Otherwise, what we would do is allocate a new array. So we get the complaint from just providing this piece of code. So the complaint here comes with a red bullet, and if I hover over it, it will tell me that, that there's a post condition that is not satisfied. So I can click on this. Clicking on it gives me the debugger. So this is not the usual dynamic debugger that you would run if you run a C# program, for example. But instead, it's a verification debugger. It's a static debugger. I have not run this program yet. I mean, you can see, I mean, there's no caller, for example. I've not run it yet. But still, I get debugging. So what this debugger tells me is what the verifier's view of the program is. Now, sometimes the verifier's view of the program may be a little bit different than yours. In that case, what you'd like to find out in this case is, what is the verifier's view? And where the difference may occur is that you may have something in particular in mind, and you have not written a precondition that's strong enough to describe that. And in that case, the verifier will imagine other states that are not within that don't fall within that precondition as well. Okay, so the blue dots here give me the various states. So I can click on these states to ask what do we know about the program in these different states. So that's like the historical debugging or time traveling debugging. Okay, so I'm interested in looking at the state here in the end because it's complaining about the post condition that doesn't hold. So let's take a look at the new log. I'm sorry, this font is a little bit smaller here. So the first component of the new log is the array. And we can see a few things about it. Let me read it to you in case you can't see it. It says that it has length 6,615. Well, why not? And it shows me two of the elements of that array, one at index 5904 and one at index 6515. Now, if you were looking in a dynamic debugger, you would see all 6,000 elements of this array, but not usually so in the case of the verifier. So here you just see some elements, and you know that the elements that are not listed are not relevant to the verification, so you don't need to look at them. Okay, let's take a look at what the input log was here, which remains the same actually. You can see that this took the else branch here. And here it's showing the element at the index 5904. And it gives me the value of it as being tick 1. Well, what that means is that it's some unique value that we will call tick 1. We don't care really what it is. It's the structure of that element is not important. And down here we see that at the same index, it's tick 2. So tick 1 and tick 2 are different. So why is that? Do you see the error in the program now? Yeah. Yeah. We didn't update the length. You mean in the record? Here it is updated. So what's not being done is we allocate a new array, but never did we copy the old elements into the new array. Okay, so let's do that. So I will write what you would probably have written as well, a loop. So what I will do is for the log array length, and I will write a loop invariant that says where what the range of my variable I is, and I will write the loop invariant that says that so far in the loop, if you take the what's in the new log from 0 and the first I elements, that will be the same thing as as in the previous log up to the same place. Okay, and what do I do in the loop? Well, simply copy. Oops, I'm making a mistake here. Okay, so I just lowercase. I'm sorry, what's the question? Wait, I'm not sure what you're asking. Are you asking about? Yeah. If we, you're talking about. Oh, you're worried about that? Yeah. Well, the invariant is that because the invariant needs to hold at the top of every loop iteration, including the very last one that we're going to jump out of the loop. And that's important because what we'd like to know after the loop here, we'd like to know at this point that I is equal to that length. So that could never be the case. What we get here, the invariant holds when you're done with the loop. So, right. So, so that is correct. And that's a thing that occurs often, actually. But let me not dwell on that anymore. OK, so what I did was I wrote a piece of code for it. And now it verifies. So now we know that the code is correct. That's good. But, yep. Yep. Because I'm using the log.len, not the new log.len, right? So in other words, I'm reading it from the old record. Yep, thank you. Yep. So I mean, indeed, I mean, that would have been another easy mistake to make, right? So if I'd written it like this instead, we then get an error. So here I've written a loop, and I had to supply a loop invariant. Now, the reason that these tools are not for everyone at this point is because you actually need to know what the tool, something about the tool. That is, you need to know something about what program verification is about. You need to know what the loop invariant is. Not every programmer does, but I'm hoping, as I said, that the next generation of programmers will actually know that, so we can write more loops that are correct. So when you use the tool, you may ask, do I always have to supply a loop invariant? And the answer is yes. But that's the wrong question to be asking. The question that you should be asking is, do I have to supply a loop? I mean, why do we have such low-level constructs in our languages today? Is what you should be asking. And there are loops. I mean, there are times that you'd like to use one. But you could also use a for all statement. So for all statement in Daphne says, take any I in this range. And now, Lucian, it is indeed strictly less than. And what I will do is I will just assign that. And I will do this all in one go. So the nice thing about this is it's not a loop. It's an aggregate statement. It does all of these things in one go. It's not the loop, so I don't need to write the loop invariant. And I don't need to have that index, the loop invariant, and figuring out where the index should be in range. I don't need to have that update to the index variable. I don't need to do those sorts of things. So you can do this in Daphne. So Daphne was designed with verification in mind. So yeah, the compiler has to work a little bit harder here, but not much. OK. Any other questions before I go on? Yeah, Brian. Yep. Yeah, it might look like that, but it is indeed a completely static checker. I've not run the program yet. Yep. OK. But thank you for that question. So, all right. So what I'll do is I'll just show you a little bit of another piece of verification that we did, Summer Intern and I and Wolfram Schulte. So CloudMake, you may know that that we're getting a new build process in the company, and CloudMake was thought last fall or last summer to be that new process that has since changed, but. So CloudMake is a modern build utility. And so because it was going to build all of Microsoft software one day, was the idea, of course, we'd like it to really be correct. So this seems like a really good application for verification. So it turns out that the way that CloudMake works is that it's a functional subset of TypeScript. And what you add to that is an exec primitive that you call out to, and that's what's actually going to, for example, invoke the compiler or the linker or what have you. So what we did was we formalized the algorithms there are several different algorithms, but we formalized two of them, and using Daphne. So we wrote those as just programs in Daphne, and so we wrote the interpreter and axiomatized the exec operation. Which is then parameterized depending on whatever tools you're using. And we proved some correctness properties. For example, that the parallel builds are correct and that the cache is working like it's supposed to. So let me just show you something from that. So here's one of those formalizations, and I'm certainly not going to give you all the details, but let me show you a few things from it. So here's the eval function. So what I'm trying to convey by showing you that is that it's a function that you could have written as well. That is, the fact that this is a formalization using formal methods might sort of scare many of you, and you might think, well, gee, I've never done such a thing. Could I really do it? Well, here it is. It's just a program. You could have written this program. And you can see the various cases. It's just an interpreter, just like you would have expected. And the interesting case is the invocation, which has to do with a few more things. And here you can see the call to exec, which is the interesting thing in this example. Okay, so the function exec is defined also in the language, in the program the Daphne program that I have here. And you can see that I'm just giving the signature of it. I haven't actually given the body of it. But I have a lemma here about it, which states some properties about it. I won't go into the details of what's being said and so forth. But it's a lemma. Usually to prove a lemma, you would have some curly braces here down below that would be a proof. And there's no such proof. So this is an unproven lemma. In other words, it's an axiom. So you have to take these properties for granted for exec. Well, so with this, we then proved the correctness of the algorithm for the things that we're looking for. Actually, let me show you the theorem. Oops, that's not the theorem. The theorem says, the theorem really just says that when you run the program, you will end up in a valid state. And if you look at the other parts, you will see why that means that you can parallelize things. But it turns out that when you axiomatize something, then it's important to get that right. Because if you get the axiomatization wrong, the whole verification, means nothing. So we proved also an existence of the functions satisfying the axioms that we've written down. And you can do that in a very program-like way in Daphne that I don't have time to tell you about how that is. But here's one lemma thereof. And usually when you prove a program, if it's a simpler program, you would just annotate it with pre- and post conditions and loop invariants, for example, and it would just prove it. Now, something like CloudMake is much more complicated. That's why we have to have all these formalizations and functions and additional lemmas, but the language supports that as well. So here what you can see is something that it uses the same for all statement, but it uses it in a proof here, but it's the same statement actually. And it uses a little calculation, which perhaps some of you have done on a piece of paper or in school. And you can see, some hints in there. You can see that here's another lemma that does a case study. Well, what is a case study? If you're a programmer, and we all are, a case study is just an if statement. You don't have to learn tactics and all sorts of complicated things. You just write a little program that does it, and you know the syntax for it already. You use the if statement. Let me point out one more thing, which is here's another calculation. And I'm giving a hint in this calculation. It doesn't really matter what it is. But what I'm going to do now is I'm going to make a change in the source program. I'm going to comment out that line. Now, this program text that I have here, I didn't look right now, but I think it's about 1,200 lines, something like that, right? So when you're developing the proof or the program, whatever it is, right, you typically have large files. And you want to be able to make progress by checking things locally. So what the Daphne IDE is doing is it's running the verifier in the background, and it does caching to figure out what the dependencies are. So when I changed something like that, it only re-verified this method. Now that still took quite a while for this method because it's a complicated thing. But at least I didn't have to spend I think it takes 5 minutes for this file, which is also long compared to a lot of the verifications. But I certainly don't want to do 5 minutes, wait 5 minutes for every change. Then we would never use these tools. So it needs to be swift when you interact with it. And if I change it back, we should see that so the purple on the side there means that it's verifying. So right now it's verifying some dependency somewhere, and that's done. Okay, so I will end here and hand it over to Chris, who will tell you more about the use of these sorts of tools, but in the Ironclad project.
Okay. All right. So Rustan just told you a little bit about the Daphne language itself, and I'm going to tell you about some of the applications that we've been writing in Daphne. can get this to go out of presenter mode here.
Or display settings.
Duplicate. All right. As you can see, several people have been working on developing secure services in Daphne here. And what we're thinking about are small critical services, not a lot of code, but something that you really want to get right and spend some effort verifying. So, for example, we're developing secure logging services. We're developing services for maintaining private databases. Like maybe you've got your medical information in a database, and you want to make sure that only small parts of this information are revealed to the outside world. We're also looking at verified password management and so on. So we've developed some basic libraries for these applications. In particular, we've developed crypto libraries for things like SHA and RSA. And we've written specs for these in Daphne. We've written code for these in Daphne and proven that the code actually meets the spec. So one thing that I want to talk about in a little bit more detail here is what happens once we've written that Daphne code. What do we do with it? And the standard answer here is that you take the Daphne tool, and it does some verification by generating boogie code from Daphne and verifying that. And then it generates some code that you can actually run by compiling it to C#. And, of course, then that C# will get compiled to MSIL. That MSIL will get compiled to x86. And that x86 will run on a platform like .NET. So from the point of view of secure services, this is quite a bit to trust here. There could be a bug in one of those compilation steps. There could be a bug in the runtime system, in the garbage collection, or threading and so on. Oh, sorry, yes, the jargon here, trusted computing base. We want to try to keep that, we want to try to keep the amount of code we have to trust for security as small as possible. So we have developed a new way to compile Daphne here that tries to minimize the amount of code that we have to trust. And we call this the Daphne Certifying Compiler, or Daphne CC. And it compiles to a representation of x86 that we can actually run through a static verifier and perform the same verification process that we did on Daphne, but at the assembly language level. So let me give you a quick demo of this. So I'm going to take the same code that Rustan just showed you here. This is a little bit of the secure logging service that Jay Lorch developed as part of, as kind of an exercise as he was developing the real ironclad secure logging service. And I'll run this through our compiler here. And when I compile this, it's actually going to first compile it and then run the verifier to make sure that the assembly language code is actually correct. And so while that's running, I will bring up the output of the code here to show you what the assembly language looks like. So I've taken the loop here where we iterate over all the elements of the array, and copy the elements from the old array to the new array. And over here, I've highlighted the x86 code that we generate. So at the top of this blue highlight here, you can see those first two lines here where it says offset log array. Those are reading out the array pointer from the data type. The next lines are actually reading the contents of the array. That's why it's multiplying 4 by the index of the array and so on. So it's reading that into a temporary register, copying it into the new array. The add 1 is when we increment I by 1. And then some of the rest of this is not so efficient code where we're spilling registers to the stack and restoring them and so on. This is not the world's greatest compiler, I'm afraid. So now if this were an ordinary compiler, this is all you would get. You get your assembly language code, you assemble it, you run it. But since this is a certifying compiler, we actually get something more here, which is we get a representation that you can actually verify for correctness. Now, I apologize in advance. This is extremely unreadable. I realize that this makes x86 code readable by comparison. This is more meant to be read by a formal verification tool than by humans. But I can point out a little bit of what's going on here. For example, this line that I've highlighted here, that is the line that moves EDI into EDX plus 4 times ECX plus 8. It's followed by a whole bunch of assertions and so on to help guide the theorem prover. So if I take this and say change EDX to EAX, in other words, if I use the wrong register here, and I try to run the verification again, I'm going to get a different result here. So this may take a little bit of time here. It's got to go through and include a bunch of libraries like garbage collection and so on. And then it'll actually attempt to re-verify this code here. And I think it takes about 15 seconds. OK. So this time, I get errors saying that some preconditions for certain calls might not hold. And I know that my code actually does not match the specification. It's not a correct implementation of the logging service. So this means that we don't have to trust the compiler anymore. We can actually verify the high-level properties of the service we're writing down at the assembly language level. All right, so hopefully this time we'll go straight to PowerPoint. So it doesn't support all of the Daphne language yet, just basic things like expressions, statements, arrays, data types, and so on. There's nothing object-oriented. It's definitely not an optimizing compiler. The only thing remotely sophisticated we have is we have a register allocator, also a linear scan allocator. All right, so that gets the compiler out of the trusted computing base. Now, what about things like the runtime system? You saw that we have data types and arrays and so on. We need some sort of runtime system to allocate and deallocate those. So it happens that we have a verified, well, a very small verified operating system called Verve that we can use for this. And this, in fact, comes with a verified garbage collector, as well as basic primitives for things like threads, interrupt handling devices, and so on. And all of these things are written in the same verifiable assembly language that I just showed you that Daphne CC generates. So we can take the output of Daphne CC, link it together with these services, and verify the whole thing as a unit. So we're actually verifying, for example, that the output of the compiler interacts correctly with the garbage collector. So to give you a little sense of what that looks like, I've just shown you a quick picture of the memory layout for the whole system. And this is an entire operating system here, in addition to the runtime system support. So it has to do OS kind of stuff like managing DMA and managing I/O and interrupts and so on. Let me focus just on the things that are relevant to the runtime system here. We have space allocated for thread contexts, for stacks, for the GC heap. And in order to prove that these things actually work, we can write down invariants on the properties of these different parts of memory. So for example, our GC is a copying GC. At some point, it has to move an object from space to space. When it does that, it has to set up a forwarding pointer saying where the object went. And we can write this down as a formal specification here of what a correct forwarding pointer means here. And I won't go into the details, but this kind of just says that, well, if you look through from space and you find something that has the format of a forwarding pointer, then, in fact, the thing it points to is a correctly formed object that has the same contents as the object that originally lived at this, in from space at this location. So our progress so far, we're not completely finished. We have most of the Daphne code written for our libraries, including big integers, rationals, cryptographic primitives. We have some drivers for a trusted platform module and Ethernet. And we have some basic services. I think the differentially private database and shrink are finished, right? Is that, OK. And we're still working on the password vault and notary service. So with that, I'll be happy to take any questions for Rustan or Brian or me. So we did at some point use a typed assembly language that had been written for the Bartok compiler. That was the original code that ran on top of the Verve operating system. So that cannot express a lot of the deeper invariants that we get from Daphne about the contents of the data structures. So usually the typed assembly language are just talking about the types of the data structures. Any other questions before?
By the way, a different answer is why didn't the other ones use this one? Well, I think that what tends to happen is that if I look at MSR Cambridge, for example, they have such a compiler for x86, right? And they did it in Coq. And I think that the reason that they did it that way is because they have experts down the hall who know Coq. They'd have to go across the Atlantic to get the experts on Boogie and so forth. And they explore different things.
Is that still the case?
V3 is not commercial, correct. But Daphne and Boogie are open. No commercial restrictions.
And we've been releasing Verve stuff under the Singularity license. The Ironclad apps is not yet on the Codeplex website, but we hope to have it there. I can give a quick answer.
I would have said, if you're going to write a piece of code and verify it, use a program verifier. Don't use an interactive proof assistant like Coq. But you can do both with both. That is, you could do, if you look at the ComCert project, that's very impressive to have done in Coq to verify a compiler correct. I'm not sure if Daphne is up to that task. But there are lots of things where Daphne is now pushing the envelope with I mean, well, does lots of induction, has functions, does co-induction even. You can have infinite structures. You can talk about lots of different things. So, and Daphne is much simpler to use. So for the things that you can use Daphne for, you would probably be able to do it in a simpler way. It's up in the air at this point.
Okay, we have time for one more question, and then we need to move on.
Yeah, I mean, you could have a bug in the spec. What you should always do is you should write a test case. Test case, not to be executed necessarily, but a test case, a test harness that's going to call the thing that has the specification that you had. To try to make sure that you have the right spec. But it could always happen. Yeah.
Potentially. One way we've been dealing with that is to have independent spec reviews. So we have one person on the team write the original spec, and then somebody else go through and sort of check it against the original FIP specification. And we have found a handful of errors doing it that way. And part of our process has been trying to figure out how to write the simplest, easiest to read specs to try and facilitate that process. On the plus side, everything that we've done a spec review for, and then the code verified against that spec, has worked successfully the first time. So it's very rare in my experience.
Okay, well, thank you guys. Yeah. Exactly.